My name is Takumi Kobayashi. I'm working at National Institute of ASD and University of Tsukuba in Japan. This video presents my work of mutual conditional probability for self-supervised learning. We propose a new self-supervised learning method. Deep neural network demands plenty of annotation information. In recent years, to address such a data hunger issue, self-supervised learning (SSL) attracts key attention. In SSL, instead of preparing laborious annotation, self-supervision and its related laws are proposed. For example, various pretext tasks are presented for learning better feature representation based on prior knowledge of images. Recently, pairs feature matching is effectively applied to design SSL laws. It uses data augmentation to produce different view samples, and then matching of paired views is considered, such as in context learning and BYOL. In this work, we propose a new SSL method to cope with multiple view samples beyond paired matching. In this method, data augmentation produces more than 2 views for each image. Then, those multiple view samples are effectively modeled in a probabilistic manner to learn favorable feature representation. Particularly, we propose an SSL loss based on conditional mutual probability of view distribution. While the pairwise approach focuses on a relationship between two views produced by data augmentation, we deal with more than 2 views. In this case, computation cost to process multiple view samples would be an issue, but we show an efficient approach using smaller size image crops as shown in the experiments. So, suppose we have multiple view samples per image which are embedded into feature space. We consider a probabilistic model over those multiple view samples. The probabilistic model leads to a loss function to be minimized for training. First, let's consider generative probability given our image I. The distribution can be described by means of kernel density estimation. Here, vector z indicates a point to probe the distribution. Accordingly, the loss is defined as a negative log probability which has a gradient equivalent to a mean shift vector. So, minimizing this loss means more seeking on this distribution, and it favors compact distribution for reducing loss. Next, we consider a discriminative probability given two different images. Those images produce view samples respectively, and the discriminative probability is formulated as a posterior probability measuring how well the two distributions are separated. So, minimization of the loss given by a negative posterior probability is equivalent to seeking most discriminative points, and thus it favors well-separated distribution. Finally, we introduce mutual conditional probability. The probability is defined as the product of generative and discriminative probabilities. It measures connection between a view sample and the image. That is, the mutual conditional probability is maximized only when there is one-to-one correspondence between the view sample and the image. Therefore, the loss of negative log probability is minimized by compact and discriminative distributions. This property is very useful for SSL because the loss leads to favorable feature representation, which is compact, increasing robustness against image distortion while well discriminating different images. In summary, these three probabilistic models are compared. The generative and the discriminative probabilities characterize compactness and separability of distribution respectively, but they are insensitive to one aspect. On the other hand, the mutual conditional probability can favorably reflect both the properties of compactness and discriminativity. Thus, the loss based on mutual conditional probability is well suited for feature representation learning in SSL. We propose an SSL method based on the mutual conditional probability model. In the probabilistic model using KDE, we apply the additional head to represent the probe point, as well as momentum model to describes distributed samples for stable training. The architecture that we use is shown in the left side, and our proposed loss is also shown. It optimizes compactness within our image and discrimination between different images. Here, we introduce temperature parameter T to control the bandwidth of the KDE and simply set it as T equals 1. In the experimental operation, we apply the proposed SSL to ImageNet 100 with version 18. We empirically discuss the computation issue regarding the generation of multiple views. Generally speaking, multiple view samples require considerable computation cost, and so we here consider 3 types of approaches to produce the multiple views in the same computation budget as a standard pairwise approach. The first one is to crop smaller size image parts. The second one is to draw additional view features from memory bank, which requires negligible extra cost. The last one is to remove the momentum encoder to produce distributed samples, which reduces computation cost by half, and thus we can double the number of views. Here is a comparison in the approaches of smaller size image cropping. The standard one is to sample 2 views of 224 pixels. By reducing the size of image patches, we can increase the number of views and find that 4 views of 160 pixels produce the best performance. It is a trade-off point between the number of views and the feature quality extracted from the image patch. Next, we consider the remaining 2 approaches of memory bank and momentum free. These 2 approaches are inferior to the smaller size cropping, whose performance is shown in the rightmost column. For reference, we also show the performance of 4 views of 224 pixels, which are the same size as the standard approach, though doubling the computation cost. Interestingly, the smaller size cropping outperforms the costly approaches because the larger size crops are overlapped to each other, making the distribution less effective for improving robustness of feature representation. At the last, the proposed SSL method is compared with the other methods on whole ImageNet dataset. These models are trained on 100 epochs. The proposed method is applied to 4 views as analyzed in the observation study, and it produces superior performance to the others. Thank you for your attention.